So where we left off, we had this canister, because it had a closed top and had a vacuum above the fluid, and the fluid on top had a. Oh, I'm using the big marker right now. But the fluid on top had an area of A1, and I poked a little hole with a super small area A2, and I said that the area of A2, it's so small, it's 1/1000th of area 1. And then we used the continuity equation. We said, well, the velocity, the rate at which the surface is moving up here, so that's V1, times area 1, right, times the whole surface area of the liquid, has to be equal to the output velocity, which we're trying to figure out as a function of everything else, times this output area. And then we say, well, and I don't remember. Let's see, I made a mistake, so I don't know if I did this in the last video or I did this in my mistake video. But anyway, so we know that the initial this top velocity times this top area is equal to the output velocity times, instead of writing area 2, we could write area 1 over 1,000, right? We could write area 1 over 1,000. We would have still had the area 1 here, and then you can get rid of the area 1 on both sides, and then you're saying that the output velocity is equal to essentially, the velocity up here is equal to the rate at which the top of the surface moves down is equal to 1/1000th of the velocity of the liquid spurting out of this little hole. So now with that, we actually have the three variables for kind of the right-hand side, the left-hand side of Bernoulli's equation. And what are the variables on the left-hand side? Well, what is the pressure at this point where we have a hole? Well, and this is an important thing. When we talk about, Bernoulli's, let me rewrite Bernoulli's equation. It's P1 plus rho G H1 plus rho V1 squared over 2 is equal to pressure 2 plus rho G H2 plus rho V2 squared over 2. We figured out all of these terms. So now let's figure out the things that we have to input here. So what is the pressure at point 2? And this is the important thing. You might want to say, and this was my initial reaction too, and that's why I made a mistake, is that, oh, well, what's the pressure at this depth in the fluid? And that's not what Bernoulli's equation is telling us. The Bernoulli's equation is telling us, actually, what is the external pressure at that hole, right? How much, when we did the derivation, we were saying how much work. This was kind of the work term, although we played around with it a little bit, right? But if we look at the water that's spurting out of the hole, it's not doing any work because it's not actually exerting force against anything. So it's not actually doing work. So when we think about the pressure, the output pressure, it's not the pressure at that depth of the fluid. You should think of it as the pressure at the hole, the external pressure at the hole. And in this case, there is no external pressure at the hole. If there was, let's say that if we closed the hole, then at that point, sure, the pressure would be the pressure that's being exerted by the outside of the canister to contain the water, in which case we would end up with no velocity. The water wouldn't spurt anywhere. But now we're saying the external pressure is 0. That's what the hole essentially creates. So we're going to say that P2 is 0. So this is 0. So this pressure was 0 because we're in a vacuum, and then P2 is also 0. So both of these are 0. And remember, that's kind of the external pressure. It's the pressure. P1 is the pressure, external pressure to the input to the pipe, and you can kind of view this as a pipe, right? I could redraw that cup as kind of like this. Well, I could redraw it as a pipe that looks like. Well, actually, no. Let me undo that. That has a big hole on the top, and it goes down some level to a super small hole like that. And this would be a vacuum, and then the fluid is just going in and spurting out at this end, right? So anyway, the pressure going into the pipe is 0, and we said since we put a hole, the pressure coming out of the pipe is 0. So we're doing no work. And what is this term? Well, this was the potential energy term, and we said that H1 is equal to H is equal to, we're saying that this is 0 height. So now this simplifies to rho times gravity times H plus rho times v1 squared. Well, v1 we said is equal to this. So rho over 2 times v2 over 1,000 squared. Right? I just substituted v2 over 1,000 for v1. That equals the pressure at the hole, the external pressure at the hole, which is 0, plus, what is H2? Well, this is H2 right here, which we said is 0. We determined that the hole was poked at height 0. So this is also 0. So that equals essentially this kinetic energy-like term. It's not exactly kinetic energy. It's rho times v squared 2. V squared divided by 2. Now, one thing that we can immediately see is that we have all these rho's on both sides of the equation, so we can divide both sides by rho. We get rid of all of those. And then we can multiply both sides of the equation by 2, and we get 2gh is equal to, plus this term, v squared, v2 squared, over, what's 1,000 squared? Over 1 million. Over 1 million. And that is equal to v2 squared. Now, we could do we could do the exact thing. We could subtract 1 over a million v2 squared from both sides, and we would get, 0.9999999 v2 squared. But let's just say, for the sake of simplicity, or let's say if this wasn't 1,000, let's say this was a million. So this surface area was much bigger. We see that this term becomes very, very, very small. And if that hole is 1/millionth of the surface area, then it becomes really insignificant. So we can ignore this term because it just makes things complicated. And we're assuming this is a really, really large number, that this hole is much smaller than that. Than the surface area of the fluid, and we this is like poking a hole in Hoover Dam, right? Hoover Dam is backing up this huge lake, and you poke a hole in it, so that hole is going to be a very small fraction of the surface area of the fluid. And you can only make this assumption when that output hole is much smaller than the input hole. But with that said, what is the output velocity? Well, the velocity is going to, you just take the square root of both sides. This is the square root of 2gh. So that is the output velocity. And what is the amount of liquid that flows out per second? Well, we figured that out already. It's kind of like a column of fluid that comes out. So per second, the length of the column of fluid will be the velocity times time, and then the cross section of that column is equal to the output area. So if I wanted to know the flow coming out, it would be the flow coming out, or the flux coming out, would be equal to the hole's area times the output velocity, and that would equal the area times the square root of 2gh. And we could use that to actually solve problems in the future if we had actual numbers. Anyway, I only have a minute and a half left, so I'll see you in the next video.